All right, welcome. Today we're going to talk about a discovery that honestly feels like it's been pulled straight out of science fiction. We are talking about using light itself to sculpt and literally rewrite the fabric of matter. It's this idea of creating stable, microscopic structures with nothing more than an intricate twist of light. So let's dive right in. So let's just start with that one big question. What if you could actually sculpt with a beam of light? I don't mean just heating something up or, shining a spotlight on it. I mean physically carving and shaping a material, imprinting a lasting pattern into its atomic structure just by pointing a light at it. It's an absolutely incredible thought, and believe it or not, it's the reality we're exploring today. Okay, so how is this even possible, right? To understand that, we need to get to know our sculptor's tool. And I'll tell you right now, this is not your ordinary flashlight beam. Not even close. This is a completely different kind of light, a form of light with a very special and very powerful physical property. Scientists call this stuff twisted light. So instead of thinking of photons traveling in a boring straight line, picture them spiraling forward in this beautiful helical corkscrew path. Yeah, it's like a tiny tornado or a whirlpool made of pure light. And this intricate spiral carries a real physical property called orbital angular momentum, or OAM. This is the key. It's not just energy, it's energy with a built-in twist. So think of it this way. A normal beam of light, right, from a flashlight, it delivers energy in a straight line. It just pushes. But twisted light, well, it delivers that same energy plus a physical torque, a rotational force, all wrapped up in its helical structure. It's the difference between just pushing something and actually being able to gently twist it open. So we have our incredible tool, this twisted light, but what are we sculpting? I mean, you can't just write on any old surface, right? You need a very, very special canvas, a material that's uniquely responsive to this gentle yet incredibly powerful helical touch. And here it is. The canvas for our art is an ultra-thin flake of a crystal called CSBIN 207. And when I say ultra-thin, I mean it. We're talking about materials that are basically two-dimensional, just a handful of atomic layers thick. This incredible thinness is exactly what makes it so sensitive and so responsive to the light's influence. So what's the secret sauce in this material? Well, it's what's called a ferroelectric. All that means is that it's filled with these tiny built-in electric dipoles. The best way to picture them is like a huge field of microscopic compass needles. And we can apply a force to point them in all sorts of different directions. And get this, the most amazing part, all of this works perfectly at room temperature. No crazy cold equipment needed. All right, so we've got the twisted light for our tool, and we've got the crystal flake for our canvas. So what happens when the tool actually meets the canvas? Well, this is the moment of creation, where light and matter interact to create something totally new. And the process itself is it's remarkably elegant. First, the scientists isolate one single, perfect flake of the crystal. Then, they cook up a highly focused beam of this twisted ultraviolet light. Now, when this beam hits the crystal, it's not a violent collision, it's more like a dance. It's a transfer. That orbital angular momentum, the physical twist of the light, is given directly to the crystal's structure. And this causes all those tiny internal compass needles to rearrange themselves, to literally follow the spiral of the light. So the light doesn't just pass through. It actually writes a pattern into the very fabric of the material. It creates these incredibly stable, self-contained little whirlpools of energy. Scientists have all sorts of cool names for them, like polar vortices or skyrmions, but what they really are, in a sense, are tiny, durable packets of information written into a crystal with a beam of light. Creating this sculpture is one thing, but that begs a huge question. How on earth do you see it? We're talking about patterns written on a canvas of atoms. Just being able to observe this microscopic art is a monumental challenge all by itself. No, really, think about that for a second. How can you possibly take a picture of something that is smaller than the wavelength of visible light itself? You can't use a normal microscope, that's for sure. You need a completely different way of seeing. And the answer is this incredible technology called Bragg coherent diffractive imaging, or BCDI. Probably the simplest way to wrap your head around it is to think of it like a CT scan. But instead of imaging your body, it's so powerful, it can build a 3D image of the arrangement of individual atoms inside the crystal. So here's how it works in a nutshell. First, the scientists fire a beam of coherent X-rays at their tiny crystal flake. As the X-rays bounce off all the atoms, they create this really complex interference pattern. It's kind of like a unique fingerprint of the crystal's internal structure. All the information is in there, but it's all scrambled up. And this is where the real magic happens. Powerful computer algorithms take that scrambled fingerprint and they just work backward. They computationally reconstruct all that data, unscrambling it to reveal this beautiful, precise 3D image of the atomic structure inside the crystal, revealing the art that the twisted light created. And what they saw? Wow. The images revealed this stunning variety of patterns. They saw these whirlpool-like vortices and even more complex 3D twists called Bloch points. It's like discovering a whole new set of architectural blueprints at the atomic level, an entire gallery of microscopic art. So, okay, creating beautiful atomic whirlpools is fascinating for sure. But what's the bigger picture here? Why does being able to sculpt matter on this insane scale actually matter for the future? Well, the really crucial point comes down to this number, about 0.8%. The scientists showed they could use this twisted light to induce up to 0.8% strain. That means stretching or compressing the crystal's atomic lattice, and they could do it reversibly. Now, that number might sound small, but at an atomic scale, that is an unbelievable degree of precise dynamic control. Let me just say that again, because it's a really big deal. We now have a way to reach into a material and change its physical structure on demand without touching it, and then change it back again, all with a flick of a light switch. This is a fundamental, game-changing breakthrough in how we can manipulate matter. And when you have that kind of control, the possibilities, they just explode. I mean, imagine computer memory that isn't just fast, but is literally written at the speed of light. Or data storage so dense you could hold entire libraries on a chip the size of your thumbnail. Or entirely new kinds of electronics built on this intimate dance between light and matter. The list just goes on.
You know, the researchers themselves really hit the nail on the head when they explained why this is such a huge leap forward. The old methods, things like epitaxy, they're rigid. They basically force a crystal to grow on a fixed template. It's kind of like using a hammer. But twisted light, it's like having a fully articulate nanoscale hand. It's a whole new level of finesse.
Which leaves us with this one final, pretty profound thought. We've basically crossed a threshold where we can use this intricate braided light to write information not just on a material, but into its very structure. The patterns we create are a new form of memory, a totally new language. And so the only question left is, what story will we choose to tell?